All right, so our next point and basically our last aspect of curve sketching that we're going to get into is what's called concavity and points of inflection. And so this is dealing with the shape of the curve, because we've now looked at the areas of increasing and decreasing of a function. We've looked at its high max and mins, the local extrema, its high points and low points. We then looked at finding all the different asymptotes and the graph's behavior around those asymptotes. And like I said, now we're going to get into looking at the shape of our curves at particular points. And we're going to use something called the second derivative test, which means we're going to take the second derivative of our function. Again, we use the first derivative to find increasing and decreasing intervals as well as max and mins. But now we're going to use the second derivative to find out whether our graph is what we call either concave down or concave up. And concave down occurs when your second derivative, and you'll see this symbol here where I have double prime, so two little marks, when it's negative or less than 0. And that means our curve lies below the tangents. And your second derivative is the rate at which your tangents are changing. And so in this case, the slopes of the tangent are decreasing, which means our derivative is decreasing, which means our double derivative is going to be negative. And again, what it means, I can draw some tangents in here. If I start at point A, our tangent would be positive and going up. Again, as we keep going on, it's positive going up. And then at the very top of our curve, the tangents are 0. That's how we know we can find a max or a min. But again, then our tangents turn to negative. And so because our tangents are constantly decreasing, that means our double derivative is going to be negative. And it means we have a concave down situation. Now the other situation we can have is the opposite, concave up. And that is when your double derivative is greater than 0 or positive. And again, that is telling us that the slopes of the tangent lines are increasing, which means the the single derivative is increasing, which means again our double derivative is being greater than 0. All right, so again, just in terms of our visual, is that at point A, we actually have tangent lines that are negative. That's not really a good tangent line for that A value. Let's see here. So we get something like this. And then, so it's negative. Our slopes of our tangents are negative. Then, of course, at the bottom, the slope of our tangent is 0. But then they turn to positive and then go greatly positive. And so, again, that means we have part of our graph is concave up. All right, now, a point of inflection, and this is key, is any point where the graph changes from concave up to concave down or vice versa. All right, so where there's a change. So if you get something where we have a curve that's concave down and then flips to concave up, that point right there would be considered a point of inflection. Whoa, big words there. Let's see, point of inflection. All right, now inflection points are just like when we're looking for max and min values. They can be found where our double derivative is equal to 0 or where our double derivative does not exist, which is another way of saying look where the denominator of a rational function is 0. All right, so now we're getting to, again, using that checklist that I put into Google Classroom, we get to example number 1. So we're going to start to graph things now. All right, now, so I'm going to do mostly everything in order, but again, I'm going to go by my checklist. All right, so if I'm going to graph the function f of x is equal to x to the power of 1/3, all right, so, or the third root of x, if you will. Now, the first step is I'm going to look for the y-intercept, just that reference point again that we've started to look for. And if the if the y-intercept's easy to find, or the x-intercept's easy to find, I'll find it as well. But in this case, let's see here. So I plug in a 0, and I get 0. So our y-intercept is also our x-intercept. So there's one point I know about the graph. Now, the second part is when I'm looking for asymptotes. I'm going to look for when the denominator is equal to 0. Well, we don't even have a denominator here. And so, in fact, there is no horizontal asymptotes to look for, vertical asymptotes to have, and there is no oblique asymptotes because we don't even have a rational function here where we have a denominator to even compare the numerator and the denominator. So there we don't have any asymptotes to worry about, which is good. Now, the second, or not the second thing, I should say, the next thing that we're going to look for is we want to find intervals of increasing and decreasing, just like we did it at the beginning of this unit, while also then finding the max or mins. Now, to do that, we got to find, and now this is the fifth thing on my checklist, so I'm going to put that in there. I'm going to find the derivative and then set it equal to 0. And so in this case, if we have x to the 1/3, the 1/3 is coming down. I have x, and then I subtract 1 off the exponent, so I get negative 2/3, which I could rewrite this function as, let's see here, I'm going to have a 1 in the numerator, a 3 in the denominator, and then again, this exponent is going to be positive because I'm putting it down in the denominator. So there's a couple ways to write that. I guess I'll go with x squared here. The 2 goes here, and that little 3 in the denominator again means that's the third root. All right, now, if I look at where this derivative is equal to 0, well, look at our numerator. Again, that's the key spot here. Our numerator is always 1. So f of x, our derivative, f prime of x, I should say, is never 0. So we have no critical points from that. But our derivative, f prime of x, should get a little space there maybe so you can see it better, is undefined though, because that's where we get other critical numbers, at x equals 0. Because again, if you can't have a 0 in the denominator there. And so that is one of our critical numbers. Now that means we're going to have a cusp or a vertical tangent going on here. All right, so I'm going to draw a chart to find out what we got going on. Oops, maybe a little bit too big there. Let's shrink that up because we only have one number. All right, so we're going to look at x equals 0. And again, our derivative is undefined there, so undefined. What's a good short form there? UD, undefined. Let's go with UD. Or does not exist. DNE. All right, so the two intervals we're looking for is I'm going to check out x is less than 0. All right, that's our first interval. And then our second interval here is x is greater than 0. All right, so again, I'm going to plug a number in to our derivative that is less than 0. So I'm going to go with a -1. And so if I get -1 squared, I end up with, let's see here, just a 1. And then I take the third root of 1, I get a 1. And so our derivative would actually be positive at that spot. All right, and then I look at greater than 0. All right, and if I'm looking at greater than 0 here, so like a number like 1 would work. 1 squared is 1. The third root of 1 is 1. And so again, we're going to be positive when x is greater than 0. Looks like I messed up my note. All right, so I get positive for both of those. Then that means that, therefore, I won't have a vertical tangent. Well, maybe I will have a vertical tangent. If I go from positive to positive, that means at cusp, you have a change of sign. So we've got a vertical tangent there. And because it's going from positive to positive, our graph is going to, again, the slopes are going to constantly increase. Then it's undefined at 0, and then it's increasing again. So it's going to look something like that. All right, now, the next thing you know, we're going to get into the specific shape of this vertical tangent. And so that's where we get into today, where we're going to start to look at concavity. All right, so this was number 6, figuring out what's going on there. And again, because there's no sign change of positive to positive, there's no max or min. If I had a negative to positive or positive to negative, there would be something going on there, but there isn't. So we don't have a max, no max or min. Maybe I'll write that in there. No sign change, no max or min. All right, and so let's see here. Now we get to concavity. What we're doing today, now we're going to find the double derivative. Number 7. And let me make sure that's on my sheet. Yeah, number 7, second derivative test. So I'm going to take the derivative of the derivative. Double prime of x. And so this negative 2/3 is going to come down in front. And so negative 2 times 1 is negative 2. And then I got this 3 times 3 would be a 9. I've got my x, and then I subtract 1 from the exponent. And so negative 2/3 minus 1 is going to be negative 3 over 3, negative 5/3. Now, if I rewrote this derivative, double derivative, I should say, let's see, I'm going to have a negative 2 on the top. The 9 is in the bottom. And then again, just rewriting that x to the negative 5/3, the 3 means the third root. Because I've switched it in the denominator, that negative 5 becomes a positive 5, and I would have x to the power of 5 here. All right. Then we get to number 8, finding critical numbers for our double derivative. And again, with this one, the numerator is negative 2. So our double derivative is never 0 as well. But just like the original derivative, it's undefined at x equals 0. So that is a spot that's important, could be a possible point of inflection. All right, so just like I did with the single derivative, I'm going to do the same idea with the double derivative. All right, so our critical number for the double derivative, again, is x equals 0. And I'm going to look at, as well, 2 intervals. Now, not often does the critical number for our single derivative and our critical number for our double derivative the same, but it can happen. That's the situation we got going on here. So I'm going to have to look at x is less than 0 and x is greater than 0, but for the double derivative. All right, and so let's see here. X is less than 0. So again, I'm going to try negative 1. Now, if I take negative 1 to the power of 5, that's negative 1 times negative 1 times negative 1 times negative 1 times negative 1. It's going to be negative 1. And then the third root is negative 1. And then times by 9 would be negative 9. Not that I care. I'm just looking at the sign here. But I'm going to have a negative on the top and a negative in the denominator, which means our double derivative here is positive. We're going to come back to what that means here in a second. Now, x is greater than 0. So I'll try like 1. Well, 1 to the power of 5 is just 1. Take the third root of 1, just 1. Times by 9, 9. Positive number. A negative in the numerator, positive in the denominator, means x is greater than 0. In that interval, our second derivative is negative. Now, I'm going to go back to my original note here. When our double derivative is less than 0, that means we have concave down. All right, and greater than 0, concave up. All right, so again, negative concave down. Let's just go with that because then we know the opposite is true. All right, so concave down, down, derivative is, double derivative is negative. So less than negative, this shape of this graph in this area, whoops, is negative, is concave down, CD. Where when it's positive here, we're looking at concave up, which again means that before 0, our graph is going to have this shape. After 0, our graph is going to have this shape. All right. Now, let's piece it together. And, one last thing here is that we have a change between concave up and concave down. So at this spot, x equals 0, which, by the way, happens to be our y-intercept here, 0, 0, because there's a change from concave up to concave down, this is called a point of inflection. So 0, 0, whoops, 0 is a point of inflection, or an IP. All right, so now I've got all this information. Now it's time to graph my function here. All right, so I have a y-intercept. It's also an x-intercept at 0, 0. There we go. Now I know that this function, when I look at number 6 here, it's increasing the entire time. And because we're going from positive to positive and x equals 0 does not exist, the tangent does not exist, we have a vertical tangent. All right, so now, but before 0, it's concave up. All right, so we have an increasing function. So again, it's just a sketch here. Kind of goes like that. Let me try that just a little bit again. Maybe make it more pronounced, because we got that vertical tangent happen right there. And there's our function. Now it's shaped like this, so I'm going to put a little CU here. Concave up. Now, going back to number 6 here, our first derivative says it's still increasing. Okay? And then my second derivative says because of it's still increasing, but it's concave down. So, still increasing, vertical tangent here, but concave down. Because it's concave down, I'm going to label it CD. And then again, this point here is important. This is an IP, an inflection point. And there we go. So not only did we find out where this graph was increasing and decreasing, we found out that there was no max or mins. We found out the inflection point. We actually found out the shape of the graph. All right, lots going on there. Again, we're going to do lots of graphing in the next week. All right, so on to the next one here. I got a little polynomial. Okay, so graph the function y equals x cubed minus 3x squared minus 9x plus 14. All right, so again, I'm going off of my graphing checklist here. And again, the first step here is just to find the y-intercept. So the y-intercept again is when x equals 0. And let's see here. I plug 0 into that equation, and it looks like I just get a 0 and then a 14. Positive 14, yeah. Now again, with this particular function, there is no numerator and denominator. Well, there's a numerator. There's not really a denominator. So there again is no asymptotes. Don't have to worry about those. We'll get to those next time out. So we got a VA, no VAs, or OAs. So we just eliminated all those. Oops, there we go. All right, so there's our first, basically, 4 steps done. We got the y-intercept, that's step 1. Each of the asymptotes is a step, so now we're on to step 5, which again is, let's find the derivative and find out where our function is increasing or decreasing, and whether we got max or mins going on. All right, so I've got y prime, finding the derivative. All right, so I've got, let's see here, 3x squared. That was, and then minus 6x. And then minus 9. All right, so I'm going to set my derivative here equal to 0. All right, so I'm going to have a 3x squared minus 6x minus 9 equals 0. This is a quadratic equation that I've got to solve, or factor by solving. All right, so I'm going to put a 3x squared here and a minus 9 here. And let's see here. I got a 3x and x will work. Two numbers that give me negative 9. Multiply. It's got to be negative 3 and 3. All right, so let's see here. Cross multiply. 9x minus 3x is positive 6x. Wrong. Okay. Got the right number, wrong sign, so let's switch. Let's go positive here, negative here. The negative 9x plus 3x, yeah, that gives me negative 6x. All right, so now I have factored this, where I have a 3x plus 3 times x minus 3 is equal to 0. All right, so what solutions would I have? If I solve 3x plus 3 equals 0, what number would work? Well, x equals negative 1 would work. And the second bracket there, well, I just plug in a 3. Oops, a 3, and that would make the second part of that bracket equal to 0. And so those are our two critical numbers. And again, because we do not have a denominator this time out, this derivative is always defined. So we're not going to get any more critical numbers for looking at the derivative. All right, now what we are going to do is step 6. Let's check out to see if we got max or mins at these spots. All right, so I've got to draw my line. All right, this time I'm dealing with two numbers. We got x equals negative 1, and we also have x equals 3. All right, so I got 1, 2, 3 intervals. All right, so we've got, let's see here. We got x is less than negative 1, and we're going to be between negative 1 and 3. And then, of course, we've got x is greater than 3. Now, because these critical numbers came from our derivative equaling to 0, there's no cusp going on. There's no vertical tangent going on. All we can have is either a max or a min, or neither. All right, so our derivative is 0 at that spot. Now, I'm going to plug in a negative 1, less than negative 1, into our derivative here. And so I'm going to try negative 2. So I like using the factored form. It makes it easier for me. So negative 2 in here. 3 times negative 2 is negative 6. So that spot would be negative. Negative 2 here would be negative. So negative times a negative, positive on this interval. So our function is increasing on that spot. Let's see. A number between negative 1 and 3, 0 works. Put a 0 in my first bracket, it would be positive. Put a 0 in my second bracket, it would be negative. So it looks like our function is negative on that interval, decreasing. All right, and then our last interval, greater than 3, I don't know, I'll go with 4. Definitely positive in that first bracket. And 4 minus 3 would also be positive. All right, so we got a positive. All right, now, let's see here. That means I have, if I'm going from positive to negative, you're increasing, then decreasing. There is a max there. And then if I'm going decreasing to increasing, I have a min there. Now I actually want to find out those values. All right, so I would plug those into my original function. And f of negative 1, I plug that into the original function way up here, this x cubed minus 3x squared minus 9x plus 14. And when I plug that in, I got 19. Again, that is a max value. And I also plugged in 3. Took me a little while, but I did it. And I got a value of negative 13. And that is our min. All right, so now I know where it's increasing and decreasing, and I know where my high spots and low spots are to plot on my graph over there. Okay, now we're on to shape, the shape of our graph. So let's see here. I guess I'll go up here, number 7. That means find the double derivative. Y double prime. So I'm going to take my 3x squared minus 6x minus 9 here and take the derivative. So I'm going to end up with a 6x minus 6. And I'm going to set the double derivative equal to 0. All right, so I got 0 equals 6x minus 6. And let's see, if I solve that, well, x is going to be equal to 1. So this is what we call a possible inflection point, right? So now, number 8, I'm going to find out if that's an inflection point. So I'm going to, again, draw my scale. And again, you can see my critical number for the double derivative this time is different than the single derivative, because we got x equals 1 here. And so, of course, now I'm going to be looking at 2 different intervals. X is less than 1, and this is in my double derivative again, and x is greater than 1. All right, well, my double derivative is 6x minus 6. So a number less than 1 would be 0. So 0 minus 6 would be negative. And then x is greater than 1, so like 2, I would make this positive. Now, if it is negative, again, without going back to my note, that means our slopes are decreasing. So it's going like this to going like this. So we're working, our slopes are positive and then going downwards. So we are concave down at this spot, at this interval. And then if they're positive, so our slopes are increasing, our slopes are increasing, not the graph. So our slopes could be negative, 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 hit 0, and then go up. That means we're concave up on this interval, which means x equals 1 is an inflection point. So that's important for me to know as well. Okay, and so guess what? I did plug that into, again, the original function. I plugged in a 1. And I got 3. And again, that is a inflection point. Okay, lots going on here. All right, so now it's time to graph this. Now, what I have to do is I got to pay attention to how high I go here, because this graph I'm not going to be able to fit on 19 and negative 13. And what else we got here? 0 and 14. So I got a high of 19, a low of negative 13. So when I set up my graph here, let's see. I'm going to go by 5s, I guess, on my y-axis. So let's go with 5, 10, 15, 20. I won't need to go higher than that because my max is 19, right? And then I got to go down to, what is it, negative 13, so that'll fit. Minus 5. So I'm adjusting my scale here. And minus 15. And the x value I can leave alone because I'm only going to 3. Yeah, 3 and 1 are the important spots. All right, now here we go. Graphing this thing. First off, I'm going to graph my y-intercept. All my points, actually. I'm going to graph my points that I know here. My inflection points, my max and mins, and my y-intercept. So those are all my reference points, key points. So 0, 14. There's the y-intercept right there. All right, max and mins. F of negative 1 is 19. F of 3 is negative 13. So I forgot already. F of negative 1 is 19. All right, so negative 1, it's up here somewhere. Right in there. F of 3, forgot again, negative 13. All right, so F of 3, negative 13. So we're looking right in here. I also had my inflection point there, which is F of 1. Which is 3. And I'm going to, well, IP there. That's an inflection point. And this is a max here. And that's a min here. Okay. So now to draw in the graph more accurately. So again, starting with our derivative test, first derivative test. Our function is going to be increasing all the way to the max. All right, now at that spot, it's still less than 0 or less than 1, so it's going to be concave down. In fact, it's concave down all the way to our inflection point. All right, so I'm going to draw this graph. It's on its way up, but I got to make sure I draw it kind of concave down. There we go. So it's increasing, 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 concave down. Now between negative 1 and 3, it is decreasing our function. But all the way to 1, it's concave down. So it's decreasing, concave down, concave down. So to know that, I'm going to put CD in here. All the little intervals, CD, it's concave down, in case I If you're not very good at art or drawing with a mouse, concave down. Now, it's still decreasing. All the rest of the way are it's still decreasing all the way to 3 here. All the way to our min. But after our inflection point, it is concave up. So it flips. So I kind of curve it like that. So that's concave up. And then after after 3, the function is increasing, but yet concave up. And there we go. And again, that's concave up. So there we go. We've got now just accurately graphed this cubic function, crazy cubic function. We know exactly the shape. We know the max, the min. We know inflection points. And we know areas of increasing and decreasing. Piecing it all together with an accurate graph. No calculator required. All right, now the last part. Example 3. A little something different here. Determine the critical points for the function. F of x equals 6x squared minus x cubed, and use the second derivative test to decide if the point is a local max or a local min or neither. All right, so this is a little bit different way to figure out if you've got a max or a min, other than doing our chart, because we're going to use the second derivative to determine that. But the first thing I'm going to do is find the first derivative. So we've got f prime of x is equal to, let's see here, I better use my pen. Let's see, 12x minus 3x squared. That's our first derivative. And again, I'm going to set that derivative equal to 0 to find my critical numbers. Again, that's where you have potential max or mins again, right? All right, so when I set that derivative equal to 0, let's see, I got 0 is equal to 12x minus 3x squared. First thing I'm going to do is, I think I can, I'm going to factor out a 3 and an x, because I can see a 3 is in common there. And so I'd end up with 4x and minus x. Or, no, sorry, a 4. And then minus x. There we go. Now, if I'm solving each piece here to find critical numbers, well, 3x is only 0 if x is equal to 0. And 4 minus x is only equal to 0 if x is equal to 4. Now, I'm not going to do a chart like I normally did before. What I'm going to now do is a little something different, just to give you an option here, is I'm going to find the double derivative. All right, and so that would be a 12 minus a 6x. All right, so now what I'm going to do is call the second derivative test to see if I got a local max or min. I know where there is a potential max or min at 0 and at 4. So what I'm going to do is I'm going to test each x value that I've got there. So x equals 0 and, whoops, and x equals 4 in my double derivative. I'll explain how that works. So it's an option. All right, so if I plug in the x equals 0 into my double derivative, well, I just end up with a 12, which is positive, which means at that spot, my tangents are increasing. They're increasing. And so that means like we'd have something like this. Our tangents could be negative, 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 hit 0, and then go up. And so that means at 0, our function is concave up at that spot. And, well, that means there must be a minimum at that spot, because at that specific spot, we know the tangent is 0. So there is a min at x equals 0, because I know the tangents are increasing at that spot, which means it has to bottom out there, and it's concave up. Now, if I test the other value there, Again, this is just for an option of how to find a max or min. I plug in a 4, I get, let's see, 12 minus 24, which would be actually a negative 12. Not that I care, the key here is that it's a negative number, which means the slopes, it's the rate of change of our slopes of our tangents, and they're decreasing, which means they were probably they are positive, and then they're flipping to negative, which means it's concave down at that area, which in our case, because that is a potential max or min, means there is a max at x equals 4. Now, just like I did before with curve sketching, if I actually want to know what that max or min is, I would plug the x value into my original function. But again, there's just another tool, another way of figuring out whether you have a max or min just based on the second derivative. Again, you could use the chart method, and we'd get the same thing. So for example, if I did the chart, we got two spots there, x equals 0, x equals 4, and you'll see that I'll get the same results here. You can determine which one's better for you. So because I don't care on a test or quiz, unless I ask you to use it. All right, so we got to look up between 0 and 4, and then we'd also have to look at when x is greater than 4. All right, so again, this would be testing my first derivative here. So let's see, less than 0, I'll go with negative. So if, again, I always like to use the factored form. Negative 1, so the first part would be negative. Negative 1, 4 minus 1 would actually be positive. So it would be decreasing on that interval. Then between 0 and 4, plug in a 1. First part would be positive. 4 minus 1 would be positive. So there we go, positive. All right, and then greater than 4, let's try 5. So that first bracket would be positive, and then 4 minus 5 would be negative, so it would be negative. And so when you're going from decreasing to increasing, there's a min here, just like my second derivative told me. And when you're going from increasing to decreasing, that means there's a max here. Again, just like my second derivative told me. So again, there's just options there in figuring out whether you have a max or a min.